While we're on the topic of reference frames that are moving, something we do want to mention is the Doppler effect is going to work for electromagnetic waves. And in Physics 242, we actually talked about how the Doppler effect works for sound waves, where essentially if I had a source that is emitting some sounds, then the wave crests are going to kind of look like this. But as the source starts to move, suppose I had a source moving this direction right over there, then we're going to get all the crests kind of piling up right over there, and it's kind of running away from its crests over here. So here we have decreased the wavelength, and here we have increased the wavelength. And if we have a source moving towards an observer, the source is going to be emitting some frequency that we're going to call F0. That's going to be this guy right over here. The frequency that a stationary observer will detect will be increased, shifted upwards, and it's going to be related to the speed of light, c, as well as the speed of the source. If we had a source and observer, and the observer was moving away from the source, then you're going to use this guy right over there. So source towards observer right here, observer towards source right here. We can actually see this when we look at stars, and if this star right here is moving towards us or moving away from us, then actually it's going to be what we call red shifted or blue shifted. Something else we kind of know is we know that the speed of light is the speed of light, and as the frequency is shifted, then the wavelength will also shift up and down correspondingly. And actually you can even see the rotation of stars, because if this was a something that was rotating, and suppose it's rotating in this direction right over here, then on the left hand side it's going to be rotating towards us, on the right hand side it's going to be rotating away from us, and so we can also see shifts in color that way as well. So we have to worry about a few more physical quantities when we start to approach the speed of light, and one of them is momentum. If you remember from Physics 241, momentum is going to be equal to the product of the mass and the velocity, and momentum does need to be a conserved quantity. We know that is true in all inertial frames. And first of all, let's talk about what does not happen. What does not happen is the momentum does not keep on going up like this. So this does not happen. What's going to happen is it's going to actually asymptote upwards as we approach the speed of light. And we can do some Lorentz transformations and kind of convince yourself that the momentum is going to be equal to gamma multiplied by the mass and the velocity. And this is actually going to be the rest mass, so the mass when something is not moving. Occasionally you'll see that as a m sub o, and again it's going to be a non-moving mass. Now what's kind of buried behind the relativistic momentum is that as we try to push something with mass faster and faster and faster, closer and closer and closer to the speed of light, actually becomes harder and harder and harder to do it. And actually any object with mass will never be able to move at the speed of light. So what's kind of happening is we introduce this new quantity, which is going to be the relativistic mass, where essentially it's going to be that rest mass. Again, sometimes it's a m sub 0 multiplied by gamma. Since we do know that gamma is always going to be larger than 1, and the faster you go, the larger and larger and larger gamma becomes, kind of what's happening is the mass is going to asymptote upwards, just like you would expect it to from the relativistic momentum sense. What we can then do is we can realize that the impulse is going to be the change in momentum, and what Isaac Newton kind of said is the force is going to be the change in momentum per unit time. What Einstein kind of said is going to be the change in the momentum divided by time, only now we're not talking about the rest mass, we're talking about the relativistic mass. So rest mass and relativistic mass. And what that kind of means is we can no longer say Newton's second law. We can no longer say that a force is going to cause a linear change in acceleration. And actually it's going to kind of matter whether the force is applied in the same direction as the velocity of the particle or not. And so if I had a particle moving in that direction right over there, and I applied a force to it in this direction right over there, then as long as they're in the same line, then what we can kind of say is that the force is actually going to be equal to gamma cubed multiplied by the mass times the acceleration. if they were perpendicular to each other, so if I had a particle, I'm going to draw my arrow a little more correct right here, moving in this direction, and I applied a force to it in that direction right over there, you're going to put a parallel, I would say that force perpendicular is going to be equal to gamma times the mass times the acceleration. Now again, since gamma is always going to be larger than 1, it's going to be really hard when something is moving near the speed of light to push it even faster. And if it's moving perpendicular, it's going to be slightly harder. Remember that it's going to be increasing the speed, because it's going to be swinging this thing around in a circle. And again, this is going to be the rest mass of the object. And something else we have to kind of worry about is as we start messing around with our mass, as we go faster and faster and faster, is we want to have to redefine relativistic work and energy. And essentially, relativistic kinetic energy is going to be written by this guy right over there. And you can kind of see that as long as gamma is close to 1, then it's going to boil down to 1/2 mv squared, kind of something that we might have seen in physics 241. And again, what happens is as we approach the speed of light, we know that we can't go any faster, so this does not definitely happen. We have to asymptote it upwards, and actually it'll approach infinity as the speed approaches the speed of light. Now, something that kind of falls out of this is as we kind of mess around with our mass, is we have to define what's called a rest energy of the system, and that's kind of the famous E is equal to mc squared. And essentially what that's saying is just by the fact that something has mass means that it's going to have energy. So I was lying to you a little bit in physics 241 and 242, where I said energy is conserved quantity. In reality, it's going to be energy plus mass is going to be a conserved quantity. So when we talk about the total energy of a particle, it's going to be equal to its kinetic energy plus mc squared. And what we're going to see in some of the later quantities, some of the later chapters, is we are going to be able to convert some mass and we are going to get some energy out of it. And we can actually relate energy, rest energy, and momentum with this little guy right down here, which is kind of like using the Pythagorean theorem. So this kind of once again leads us to the ultimate speed limit of the universe, and what Einstein realized is that energy or mass, they are kind of interchangeable, cannot move faster than the speed of light, or 3 × 10⁸ meters per second. And even if something had mass, in order to reach c, it would require an infinite force and it would have an infinite energy, and that would be unattainable. Now when we talk about light, we've talked about the wave nature of light in physics 242. We can talk about kind of little chunks of light, and we're going to call these chunks photons. They can move at the speed of light because they have zero rest mass. They have essentially an m0 that is equal to 0, and light can move at the speed of light. Now, they actually have to move, these little chunks of light, as we can treat them, they have to move at exactly the speed of light. They cannot go any faster. Now, they also can't sit still, because then their energy would go to 0 because they have no momentum. So let's go ahead and take a look at an example of this. 37.10 says if you have an electron, what is its rest energy? And so the rest energy is going to be equal to mc squared. And so we know this is going to be 9.1 times 10 to the minus 31 kilograms for an electron. This is going to be 3 times 10 to the 8th meters per second, and don't forget to square that guy. And the energy is going to be equal to 8.19 times 10 to the negative 14th joules. And up until this point, I've always said work in kilograms, meters, seconds, and everything like that. In physics 243, we are going to talk about a new form of energy, and that's going to be an electron volt. This was originally introduced in chapter 23, and what we're going to say is 1 electron volt is going to be equal to 1.602 times 10 to the negative 19th joules. And essentially, if you remember, if we had a potential that was a 1 volt potential, so 0 volts and 1 volt, and we took an electron. If we were to drag this guy, we did some work to it, and that is going to be 1 electron volt, how much work it takes to move that amount of charge up by 1 volt. And because we're dealing with really small energies very often in this chapter, or in Physics 243, we are going to work our energies in electron volts. So we can say 1 eV is 1.6 times 10 to the negative 19th joules, and we're going to get 511.875 electron volts, or we could even say this is going to be 0.512 mega electron volts, and this is just a lot more palpable than this 10 to the negative 14th. So we will be dealing with electron volts fairly frequently in this class. And it's definitely worth saying this again. We are going to see electron volts, unit of energy. 1 eV is equal to 1.6 times 10 to the negative 19th joules, and really important. So I do want to finish off a little bit and talk about general relativity. And before Einstein, Newtonian mechanics worked, and it worked fine. And there's absolutely nothing wrong with it, especially if we're talking about speeds that are significantly lower than the speed of light. However, Newton's laws, while they're not wrong, they are incomplete. Relativity came along, and so we had to kind of generalize it. And when we talk about general relativity, that's where that kind of comes from. Now, as we come up with newer theories in physics, we do have something called the correspondence principle, which says, okay, if you used to be able to explain something, and something new comes along, you need to be able to explain both of the phenomenon. So what Einstein has kind of done is he's changed our knowledge of time and of space, and he's created this thing called space-time that can kind of bend. Time can dilate, mass can appear to get heavier. And when we talk about the general theory of relativity, we have to, kind of say, can it explain all of these things as we mess around with mass and speed and even gravity to some regards. And what I kind of mean by that is if we can't distinguish between whether we're in a moving reference frame or not, does it make any difference whatsoever? For example, if we had a astronaut that was in a closed capsule, no windows, anything like that, and he dropped an object and it fell down to the ground, then he could be on Earth. It could be accelerating downwards at g. Or the astronaut could be somewhere out in space and be accelerating. So here he's accelerating upwards at g, and if he drops something, he's going to make the same observation. And I mean, the question is does it really matter? And no, it does not.